Okay, this next series of videos is going to be taking a look at your graphs in the polar plane. Literally, we're going to be graphing just like we did in the Cartesian coordinate system. And I'm not talking plotting. We did that last time, where we plotted an ordered pair, say 3, -60 on the polar plane. Well, we're going to be plotting points, but several of them related to a certain equation, an equation that we would say a polar equation. So just to kind of refresh your memory, back in Algebra 1, you would be asked to graph something like this. Now, back in Algebra 1, this relates the x and the y variable. It says what y is 2 times the x coordinate minus 5. So if the x coordinate was -3, for example, 2 times -3 is -6 minus 5. The y coordinate would be -11. There's a relationship between the x and the y coordinate. And, obviously we could pick any value we want for x. Any real number would be fine. Multiply it by 2, subtract 5, and we get the corresponding y coordinate. If we were to plot every single point, every single relationship, every relation here, it's not like we would get a bunch of random dots all over the Cartesian coordinate system. We know now, I'm not going to plot a bunch of points. I'm just going to use the slope and the y-intercept to kind of demonstrate this. So here's the y-intercept at -5. The slope is up to right 1. This line represents every single solution to this equation. Every single point on this line, no matter what it is, decimal fraction, radicals, it makes no difference. Any point on this line will solve this equation and represents a point in the relation. Well, we can do this same sort of thing in the polar coordinate system. In other words, there are polar equations. It's just we're not going to be using x and y. We're going to be using the r and the theta. So we can show relationships, for example, between the r and the theta. Now, even though r is our first coordinate, a lot of times these are solved for the r variable. So r equals, say, 3, or r equals 5 cosine theta, or r equals 2 minus 4 sine of theta. And we could just say r equals 3 theta, for example. These are all examples of what we would call polar equation. It's a relationship between the r and the theta. And again, notice we're solving for the first coordinate. We're not thinking in terms of functions anymore. Very rarely do you have something that would qualify as a function, and functions don't really exist as far as, passing a vertical line test, because that's relative to the Cartesian coordinate system. Since we're in polar coordinates, we don't really consider functions, but we do like to solve for r quite often, whenever possible. I mean, sometimes it's not easy to solve for r, sometimes it's not even possible algebraically to solve for r, but we would like our equations solved for r. So we are looking at a relationship between r and theta. Right? So if we were to take this one, for example, maybe this one would be an easier one to start with instead of the trig. For example, if theta was, and this seems kind of backwards from what we're used to, if theta was 5. Theta was 5, our r coordinate would be 15. So we would plot the ordered pair in the polar plane, 15, 5, and that would be maybe considered radians. I don't think we would go with degrees there, right? We would consider that as 5 radians, whatever that is, right? Something like this. We'd say, okay, what's one point in this relation? Again, since we have it solved for r, it'd be much easier to substitute in a value for theta. So pick a value for theta, something easy. That should be easy, 60 degrees, because the cosine of 60 is a half. 1/2 times 5 is 5/2, or 2.5. So we would plot the point in the polar plane, 2.5, 60, and you know what that would look like. This is freehand. Like I said, this never goes well. Here's your pole, here's your polar axis, 2.5, 60. Well, here's 1, here's 2, here's 3, 2.5, and then 60 degrees in the counterclockwise fashion. So it would be on the circle, goodness, on the circle of radius 2.5, 60 degrees, wherever that would be, maybe right about there in the polar plane. 2.5, comma, 60. So what we're going to do is, in the next videos, take a look at actual named polar equations. Right? Like, for example, this guy has a name, r equals 3. There's a name given to this, just as y equals x squared has a name, or y equals the square root of x, or y equals absolute value of x. This is called a quadratic function. It has a shape that is a parabola. This is the square root function. This is the absolute value function. Polar graphs have names as well. We're going to talk about those and look at the relationships between the numbers and what we have here, and kind of get an idea of what these things are going to look like before we even go to graph them. And yes, we are going to physically plot these point by point, just as we did lines and parabolas and stuff back in Algebra 1. Right? So before we get too far involved, it might be a good idea to have your calculator by your side. This is a great tool when dealing with the polar graphs here, because it can give us a quick graph of things that are not exactly super easy, to say the least. So your calculator will be a great tool for you to see quick graphs of what these polar equations look like. All right, but before we begin here, go to mode on your calculator. All right, and then in the mode menu, you have all these choices. Let's change, mine is in radian if you notice. Let's change that to degree first, before I forget. There will be certain graphs that we will want to do radians, but they are few and far between. The next thing, the big thing, notice that fourth choice says function. It's flashing on it right now. Actually says FUNC. Well, I'm going to scroll across, not to par, not to sequence. I'm going to scroll across to pole, and 3 guesses what that is. Right, so scroll across to polar. You do have to hit enter, so it is highlighted. Right, and then now everything you graph will be a polar equation. Now get ready for the magic. Go to y equals now, where you would normally graph, and golly, it's not y and x anymore. It's r and theta. So let me clear that out there. I didn't mean to have that there. So again, solve for r. We're not saying these are functions by any stretch of the imagination, but when you hit your variable button, you know, when you would normally do the x, this isn't working very well, hit the x and it's not x anymore, it's now theta, which begs a question, or answers a question, I suppose. Why was that button called x, comma t, comma theta, comma n? Because it depends on what mode you're in. Well, we're in polar mode now, so everything's in terms of r and theta. Your variable will be the theta. Okay, so let's clear that out of there. Don't want that function there. So clear out, clear out. There we go. Next thing, go to window. Very important to set your window. You notice there's 2 choices at the top, or more choices I should say, but at the top you have theta min. That means when the calculator starts plugging in values for theta, what is the smallest value you want the calculator to plug in? So I usually go with 0. In fact, it'd probably be wise to write these up here. So for the first choice where it says theta min, I'm going to go with 0, and we are talking degrees. You don't have to put a degree symbol. It will assume we're in degree mode. Theta max, this is not random, 360 degrees, 1 full revolution. So we're going to graph going around, you know, degree-wise and hit a full revolution. And then the last one is theta step. This is actually pretty important, this theta step, because when your calculator graphs, it's only going to plot the points at each step of the way. So you're going from 0 to 360, and if you want to count by 30s, well, it's going to plot 0, and then see what happens at 30, 60, 90, 120, etc., till it gets to 360. The problem is, if your graph is a circle, and you don't do a small enough theta step, your circle could actually look like a hexagon. And don't be fooled. It's definitely not a hexagon that you're working with, but your calculator is only going to plot the number of points that, 30 would divide into 360, along with starting with 0 and hitting 360. The calculator is only going to do so many points. So if your graph starts to look choppy, very linear, sharp points, it's probably not correct. Your theta step is a little too large. So let's kind of compromise here. I'm not saying 15 degrees is the magic number, but I'm going to go with 15 degrees. If my graph looks a little too choppy, then, we'll make a smaller number like 7.5. It doesn't have to be, keep cutting in half. You can go with smaller ones. But be careful. Don't say, well, let's just make this 0.01 and make the calculator plot a bunch of points. It will take the calculator a long time to go through the graph, and it will slowly trace it out because it's having to plot so many points. So let's keep this reasonable at 15 degrees. Then X-min, X-max should be familiar, and X-scale are your next choices. These are exactly what we would think of in terms of the Cartesian coordinate system. Because we're in polar coordinates, true enough, but it's really sizing up your window left to right, up, down. So this is, like I said, Cartesian coordinate information, but it's kind of helping you out with this calculator, with this rectangle here. So we do need to actually pick appropriate so we can see these shapes, how wide and how tall. So for these, I'm just going to go an X-min of -8, X-max of 5, X-scale of 1. And then the Y-min, Y-max, and Y-scale. What do I have here? Looks like I have -5, +5, and 1. Again, there's no magic to these numbers. It's just for the graphs that we're going to do. This should be good enough to fit in things. And again, you know how when you graphed in the Cartesian coordinate system, sometimes your picture was off the screen. You would have to alter your window here. So under window, I would suggest you put these in so we're ready to hit the ground running on the next video with our actual graphs. So make this your viewing window, and that should be good. If we need to adjust it, and there's a couple that we will need to adjust, we will do so. All right.